Okay, let's continue. We have then the point estimate is x1 minus x2 is equal to 172 minus 166 is equal to 6. Now, the next one is to, it says sigma 1 is equal to 12 and sigma 2 is equal to 12. So the standard deviation for both populations are equal to 12. What is the test? The statistics. Okay, it's x1 minus x2 bars minus 0 divided by what? Divided by sigma 1 squared divided by n1 plus sigma 2 squared divided by n2 square root, and that is equal to 6. x1 minus x2 bar is equal to 6 divided by 12 squared divided by 60 plus 12 squared divided by 50 square root. So 12 squared divided by 60 and 12 squared divided by 50 square root, and this is 6 divided by 2.3. Okay. Okay. 6 is equal to 2.61. Okay. So what is that mean? 2.61. That is my test value, and I'm going to compare it with the critical value over here. And my test value is 2.61. 2.61 is approximately right here, and is in the rejection zone. So my statistical conclusion is based on this data. We do have evidence to reject the null hypothesis, okay, or accept the alternative hypothesis, and it means that really the length of the games really are shorter for the 2003 season. So we reject the null hypothesis and we accept that really there is a the seasons 2001 last longer than the seasons 2003. Okay, they want us to provide a 95% confidence interval. Okay, and it's very easy. Let me do it in here. The 95 confidence interval. Okay, D. 95% confidence interval is equal to x1 bar minus x2 bar plus or minus z of alpha divided by 2 times what? Sigma 1 squared divided by n1 plus sigma 2 squared divided by n2, and so we know that is 6 plus or minus c of alpha divided by 2. If we are dealing with 95% confidence, interval is 1.96 times this that we already have is 2.3. And that is equal to 1.96 times 2.3 is, no, here's one piece. Times 2.3. 4.5. So it's 6 plus or minus 4.5. That is like 95% confidence interval. Something that we need to check in here is the 1.96 over here, and we did have in the hypothesis testing the 1.645, and these are different. Why? Because this is 0.05 and this is 95% confidence level, so we are dealing with 0.05, 0.025 over here, and 0.025 over here. So we are dealing with, there is a difference between the hypothesis testing, because it was an upper tail test, and this is confidence interval, and we need to use this 196. Okay? And I think that they also ask for the 99% confidence interval, and it's exactly the same, but instead of using 1.96, you have to use the 99. that is 2.576. That's the only difference. Okay, now let's continue with the chapter. The next section is exactly the same thing. However, in this section, we do not have the standard deviations of the population. We only have the standard deviation of the samples. So sigma 1 and sigma 2 are unknown. It's exactly the same, but instead of using C, the standard normal distribution, we have to use the T distribution. That is, the one that we should use in order to assure that we are dealing with this. Okay, and the confidence interval is exactly the same thing, 1x1 bar minus x2 bar plus or minus. Instead of using T, we're going to use T, and instead of using sigma, we have to use the standard deviations of the samples, S1 and S2, but it's exactly the same thing, Now, when we were dealing with one population, we have to say that the degrees of freedom is the sample size minus 1, and we saw that in the previous chapter, chapter 9. But in this case, we do have two populations. So how many degrees of freedom? Okay. Usually we do not have the same number on the samples. So we have to compute the degrees of freedom, and that is a formula that is huge. That's on page 416, and that's the formula 10.7. That is a chorizo-like formula, if you will, and there are many things that you can do. There are many mistakes that you can have over there. I pretty much agree with that. However, that is the only way to calculate how many degrees of freedom. And when you get the degrees of freedom, you have to round down, okay, for the degrees of freedom. Why? Because the lower the degrees of freedom, the fatter is the distribution, so it gives more confidence in your assertions. That's it. And therefore, hypothesis testing is exactly the same thing. Exactly the same thing, so that's it. Okay? We do have some situation where we may assume that sigma 1 is equal to sigma 2. Sometimes we can do that. Sometimes we can say that the standard deviation of the population 1 is exactly the same as the standard deviation of the population 2. And in that case, we can work this less complicated. Why? Because in this case, and only in this case, the degrees of freedom is n1 plus n2 minus 2. Okay? So n1 plus n2 minus 2 are the degrees of freedom that we're going to use in the test statistic, and we have to compute a pool sample distribution or a pure sample standard deviation that is equal to n1 minus 1 times S1 squared divided by plus n2 minus 1 times S2 squared divided by n1 plus n2 minus 2, and this is the square root of this. And instead of using S1 and S2, we're going to use SP. That is the pool standard deviation for the two samples, if you will. And that's it. That's it. But only when you can say that the two standard deviations of the two populations, 1 and 2, are equal. That's the only time that you can use this formulation or this formula for the degrees of freedom and this standard deviation of the two population, of the two samples, the pool sample standard deviation, and then you're going to use it here. And that's it. And of course, when you are dealing with hypothesis testing, your test value is going to be x1 minus x2 minus d0 divided by what? S1 divided by n1 plus s2 divided by n2. That's it, right? Is it squared? It's squared. Sorry about that. It's squared. S1 squared divided by n1 plus s2 squared divided by n2. That is the test statistic that you are going to use in order to compare with the critical values depending on the degrees of freedom and so on and so on and so on and so on. Okay, that's it. Let's do one problem. Okay, let's do problem 14. Let's do problem 14. Again, you are going to use the simplified formulas only when you can say that the two standard deviations of the populations are equal. However, it's hard to find that situation in real life because you do not know the standard deviation of the population. That's why you are using this process, this procedure. Okay, let's do problem 14. Problem 14 says, are nursing salary in Tampa lower than those in Dallas? So we're going to compare Tampa and Dallas, Texas. Tampa, Florida and Dallas, Texas, the nursing salaries. We have in Tampa, N1 is equal to 40, X1 bar is equal to $56,100. That's the mean salary for the nurses in Tampa. And S1, the standard deviation is equal to 6,000. In Dallas, we have a sample size of 50 nurses, and the mean salary is $59,400, and the standard deviation on that particular sample is 7,000. Okay, formulate the hypothesis such that if the null hypothesis is rejected, we can conclude that salaries for nurses in Tampa are lower than those in Dallas. So we really need to put in the alternative hypothesis that the Tampa are less than the mean salaries in the Dallas population. So this has to be in the alternative hypothesis. So how we formulate this? The mu1 minus mu2 is less than 0 against the null hypothesis that mu1 minus mu2 is greater or equal than 0. In this case, we do have a lower tail test, okay? And we are going to use T, and they said use alpha equal to 0.05. Okay, how many degrees of freedom? First of all, how many degrees of freedom? In order to find out what is my critical value over here, I need to find out degrees of freedom. In this case, we do not have that assumption that the standard deviations of the two populations are equal. So we have to use the chorizo-like formula on page 416. So the degrees of freedom is nothing but S1 squared divided by 1 is 6,000 squared divided by 40 plus 7,000 squared divided by 50. Everything squared divided by what? By 1 over 39. 39. Why? Because it's 1 over 1, n1 minus 1, and n1 is equal to 40. times it's 1 squared, 6,000 squared divided by 40 squared plus 1/49 times 7,000 squared divided by 50 squared. Okay. I already did this, and this chorizo-like formula is going to be equal to 87.55 degrees of freedom, so we're going to use round down 87 degrees of freedom. Okay? Okay. So for the 87 degrees of freedom, we have to look for the critical value. And the critical value over here for this one is 0.05. 87 degrees of freedom is negative 1.663. 87, yeah, 0.05, negative 1.663. That's my critical value. Now, we need to compute the test value. And that test value is x1 bar minus x2 bar divided by what? By this. The square root of 6,000 squared divided by 40 plus 7,000 squared divided by 50. Okay? And x1 minus x2 is what? 56, 100 minus 59, 400 is negative 3,300 divided by this, and this I already have it, is 1371.13, I guess, and that is a negative 2.4. Okay, so negative 2.4. Over here, in my critical value that is negative 1.663, I have this 2.4, negative 2.4 over here. So we do have this test value in my rejection zone. So we reject the null hypothesis and really conclude what? That the Tampa salaries are really significantly lower than the Dallas salaries for nurses. That's it.